So today we're going to be looking at van der Waals equation of state. And van der Waals equation of state is our pressure equal to R times T divided by, this is our R constant, our temperature, divided by V minus B. Our V is going to be our molecular volume, and our B is going to be the volume that our atoms and our molecules take up. And then it's going to be subtracted by A, our attraction constant, and divided by the volume squared. So this is our van der Waals equation of state right here. And this portion of it is just a reworking of the ideal gas law that we already know about. PV equals nRT. And this is the only thing we're adding. We're just adding this attraction constant here. On our pressure versus volume graph, the way this is seen is we're going to have our pressure versus volume changing, and it's going to do this, and we're going to have our points of inflection right in the middle here. And so it's going to change depending on our equation, depending on our attraction constant, and everything we need to do. Now, these points of inflection are going to help us out. So we get these points of inflection when we set the second derivative of this equal to 0. So what we want to do is we want to find the first derivative and the second derivative. And this graph is going to help us also on our pressure versus time graph. On our pressure versus time graph, you're going to have all of these being our critical points. This is going to be our critical point, and anything after that is going to be a critical value. So what we want to do is we want to find the first and second derivatives of this equation right here. So to do that, it's going to be dP dV, and it's going to be equal to it's going to be negative RT over our V minus B squared. It's on the bottom, it's negative 1. And then minus again, or 2A divided by V cubed. You can see how I did that. So this is going to be our first derivative. And then let's do it again. Let's derive again. So it's going to be our second derivative. It's going to be our second. Can you see that? Yeah. Okay. That's going to be positive RT over our V minus B cubed minus 3A over V to the fourth. So now we have our first derivative, and we also have our second derivative of this equation, of our first equation. And what we can do is we can set these equal to each other. So we can subtract here and subtract here as well to find our A's and B's. So let's do a little bit of that. So we can say for the first derivative, we can say our negative RT, our negative RT over V minus B squared can be set equal to 2A over V cubed. So we can set them equal to each other to find our unknowns. And we can also say RT over V minus B cubed can be equal to our 3A over V to the fourth. It's a little hard to read, but what we're doing is we're just adding this over to the other side so we can solve for our unknowns. And after this, what we want to do is we want to make sure we're using our critical values. So on our temperatures, we want to make sure our temperature is critical, our volumes are critical, just so we're using the correct values that we want when we set our second derivative equal to 0. Yes. Okay. Perfect. And now what we can do is we can cross multiply. We can cross multiply these equations. Let's keep it more fast. So now what we can do is take our first derivative and multiply by the reciprocal of our second derivative so we can solve for b. And so to start with that, we can say our 2a times our v critical times to the fourth over our 3a, the reciprocal is down here, of our v critical to the third. And so these can cancel out. So we can say 2a minus 2a, 3a just goes to 2/3. And these just go to 4 minus 3 just goes to 1 volume critical volume. And then we also have our negative RT critical divided by our normal RT critical, extend it, and we have RT critical. Okay, yeah. And then we have our, up here we have our volume critical minus b cubed over our volume critical minus b squared. And I want to change this as well. This is going to be squared to the outside. And so these can cancel, and these can cancel, 3 minus 2. And it should be negative volume critical minus b to the 1 power, So this would be our simplified equation after multiplying the first derivative by the reciprocal of the second derivative. Now we can find our a and b values, but first it looks like we want to find our b value. So let's do that. So let's find our b value. Let's find out what this is going to be. So we have this 2/3 VC minus our VC here. So it's going to be 2/3 VC equal to VC plus B. And we can subtract 1 VC from here. So 2/3 minus 1 is going to be 1/3 VC equal to B. Yeah, 1/3 VC equal to B. So that's going to equal B. And using B, we can find A from the second derivative. Okay. So we have B, and then our second derivative, again, is going to be our negative RT over V minus B squared plus, it's going to be plus, it should be our 2A over VC, or VC cubed. That should be our second derivative. So there's our second derivative, and what we want to do is we want to plug in b. So we're going to say negative RT over V minus, or VC, sorry, VC. Well, these should be C's. VC minus 1/3 VC and then squared. That should be squared. Plus, or you could say equal to, so you subtract to the other side, equal to, if we erase this negative, we can make this positive, equal to our positive TA over VC cubed. Okay. Now we can solve for our A. So down here, RT over VC 2/3 VC, RT over 2/3 VC squared, sorry, this is going to be squared, equal to our 2A VC cubed. And keep going with that. We have, this is going to be not 2/3 VC. It's going to be 2/3 VC squared, which is 4/9 VC squared. So now we can cross multiply to find our A. And so it's going to be 2A times our 4/9 VC squared equal to RT VC cubed. RT times VC cubed. So what we want to solve for is our A value. So we can divide all of this. So now we have, I'm going to write it up here because we're already done with this. So coming back up here, we have 2A equals our RT VC cubed all over, and you can just say, or I guess say times 9/4, and then VC squared is going to be on the bottom here because we're dividing. And then you can divide again by 2, by this 2A. So that's going to go, so times 1/2 you can also do. And that gets rid of this to find our A value. This is our A value, but let's clean it up a little bit. Let's clean it up a little bit and say A is equal to RT VC 3 minus 2, 1. Let's put this out front. So let's say 9/8 RT VC is equal to our A. And this is our A value, and then we've already found our B value earlier. We found our A, and then our B we also found as 1/3 VC. So we have our A's and B's. We don't need these. So we have our A and B, and then we have our original equation, which is our pressure is equal to RT over V minus B minus our V minus V, and then our VC squared, and up here is our pressure, volume. Our A. Our A right here. So now what we can do is we can input, this is our critical equation. So now we can input our A's, or our A and our B into the equation to find the compressibility factor that we need. So we're going to say the pressure, the critical pressure equal to R times the critical temperature of the critical volume minus our B, which is 1/3 critical volume, 1/3 critical volume is going to be subtracted by our A up here, 9/8, our T, critical volume, these are all critical, divided by our VC squared. Okay, then we can simplify from here. And now that we've inputted our A and B, we can start simplifying this equation. So our PC is going to be equal to, it looks like we can factor out this RTC VC that's in here. So let's do let's simplify a little bit more beforehand, but we have RTC over VC, 2/3 VC, minus 9/8, or R constant, temperature critical, and over just one critical volume, because these can cancel out. This VC right here and this VC. There's one up here and two down here. So now we can take out this R critical temperature and critical volume up here. We can say that our PC is equal to our R critical temperature over our critical volume, and then have, I believe, 9/8 or 3/2, because you flip the reciprocal, so 3/2 minus 9/8. So we have this, and so to get this is going to turn into 3/8, and we multiply that VC on the other side and divide by our RT. We get critical pressure, critical volume over R times critical temperature. And this is going to help us because this is going to be our compressibility factor. This is going to be the way we find Z, because PV over RT is equal to our Z right here. This is equal to our Z, and this usually equal to 1, whatever the compressibility factor is. So we can take this 3/8 and replace our PV over, we need to solve for VC so we can replace all the VCs in the A and B with the correct 3/8 to find the actual numerical values for A and B, not just with the volume. So let's do that. So we can erase this. So we can find VC by multiplying again, or just dividing by that critical pressure. So we can say V critical volume is equal to 3/8 times RT over critical pressure. So we can replace this into A and B. So B is going to be 1/3 times 3/8 times 3/8 times C over, and we're just going to have B equaling 1/8 times C over critical pressure. That's going to be our B. And our A is going to be 9/8 times R times critical times our VC, which is our 3/8 RTC over PC, and that's going to turn into, this is going to be over 27 over 64, could be a little more simplified, R squared times critical temperature squared over the pressure squared. So this is going to be our A, and this is going to be our B. The numerical B values and A values that we find. So no matter what gas you're going to have, you can use these A and B values and the compressibility to find what you need. And it doesn't matter what gas it is. It could be water, carbon dioxide, hydrogen, whatever you need to find on those values on the second derivative graph, those points of inflection on the pressure volume graph and all of the critical points on the pressure temperature graph.